Okay, so welcome back, everybody. Um, so picking up from yesterday, first thing I wanted to mention, there's a specific example that I was going to kind of gloss over. I'm not going to actually fully do. If you want to see how this is done, the best thing to do is you can read in the electronic copy. This is like pages 31 and 32-ish, 31 through 33. So if you read pages 31 through 33 in text, uh, or really this is section 2.2.4. What this describes is transport equations in three space dimensions. So uh, transport equations in three space dimensions with constant velocity. So here's how I'm going to write this. So the PDE in question is the following. So recall the original transport equation, right? So the original transport equation is like this, right? So here's my original transport equation. This is in one dimension, right? So this is like the one-dimensional transport equation. So in three space dimensions, what would the analog of this thing be? It would be u sub t plus a1 u sub x1 plus a2 u sub x2 plus a3 u sub x3. And if it's inhomogeneous, this right-hand side would be 0. Meanwhile, my auxiliary condition or initial condition here in this case specifies a signal to be transported in this way. Now, of course, the big problem here is I can no longer easily kind of visualize what it is that's going on here, right? So before I was able, for a transport equation, I was able to um, draw a like a profile here for fixed t that showed me how, like, say, a signal would be transported, or like a wave would be transported here. So this is, this is not going to be as easy to visualize. And if I seek to solve this on some omega, which is like the set of all x1, x2, x3, t, such that t is greater than or equal to 0, um, then this is my three spatial dimension transport equation with constant velocity. So the thing is that this can be rewritten kind of in a nice way. So if I let A be the vector, the textbook likes to use the like curved brackets here. It's kind of like physics notation here. Whenever, I'm not going to use that typically. I'm just going to use the normal parentheses for these. So, confusing vectors of points, I'm not too worried about that. So here's my vector A. So if I write my vector A like this, I can easily rewrite this in vector form. So this PDE can be rewritten as u sub t plus A dotted with the gradient of u, where our gradient here, of course, is the spatial gradient, right? It doesn't include the t the t slot here. So this is equal to 0, and then I have the same auxiliary condition, but I'm going to combine these three as a vector x 0 is equal to g of x here, where x is this vector X is this vector that contains the three spatial independent variables, right? Okay, so this is a shorthand way of writing this, and we're going to do this kind of thing over and over again in this course, right? Typically, this is going to be an easier thing to deal with conceptually. So it turns out if you read these pages I indicated, you'll see that straightforwardly method characteristics, we saw yesterday how to do that for the case where you have more than just two independent variables. So method characteristics immediately yields a solution here. So this solution is so this is method of characteristics yields the solution, which is g of x1 minus a1t, x2 minus a2t, and x3 minus a3t. But if you'll notice, rewriting this in this vector notation, this is really just u of xt is equal to g of x minus at, where the t is just a scalar thing multiplying this vector a. But hey, that was actually my solution that I originally found to this transport equation from way back, right? Okay, so this is a transport equation for constant velocity. Now, here, this was an inhomogeneous transport equation because this right-hand side was 0. We can consider the inhomogeneous transport equation. So let's do that really quickly. So what if I do an inhomogeneous transport equation? So very, very quickly. So this is inhomogeneous transport equation in 3 spatial dimensions with constant velocity. And what this looks like is u sub t plus vector a dotted with the gradient of u is equal to f for some function f, and u of x0 is equal to g of x. So again, via method of characteristics, and especially because this is a linear equation, this works out very nicely. That our general solution, I'm not even going to write the one that's not in vector notation. I'm just going to go ahead and write this in vector notation. This is u of xt is because for the method of characteristics, right? So just let's think real quick about what's going to happen. So for the method of characteristics, here my characteristic equations for the x1, x2, and x3 part of the characteristic equations, those are going to be very easy because those first derivatives are going to be equal to constants in each slot, so it's going to be a very easy ODE system to solve. I can just solve it one at a time. And then the z, right, and I should say the t characteristic equation here, that is 1, so these characteristics can be thought of, with t being the parameter, right? That's what we kind of always did for a PDE that has time as an independent variable. And then the last characteristic equation, the one for z, is going to be simple. It's just going to be 0, and it's going to lead to, like I said, the easiest possible ODE to solve. Well, the exact same thing is going to happen in this case, except for the z characteristic equation, I'm going to have this f. But it's going to be just like a very, very simple ODE, something like this, right? It's going to be that. Oh, I'm off the screen. Here we go. It's going to be this, which I can solve just by explicitly integrating, right? So I get a constant of integration, which is going to be my G, but it's just going to be integrating this thing. So it actually tells me, based on this and what my solution was for the homogeneous case, because this is linear, this is going to tell me exactly how this works in the inhomogeneous case. So the actual general solution here, again, if you're confused about any of this, just read this section that I outlined. So this is the integral from 0 to t of f of x minus a times t minus a dummy variable called theta d theta plus g of x minus at. So this is my solution to this thing. Okay, and again, like I said, if you're slightly confused about any of that, just have a look at that section. The nice thing about this is that we can immediately move into, so section, we are going to skip this, but you can read it if you want. Here, maybe I'll just say read on your own. It's not going to be important for our concerns yet. I may come back to it later, but this is section 2.2.5, which is the transport equations in three spatial dimension with space varying velocity. So transport equations in three spatial dimensions with space varying velocity. This involves some identities that we will be very, very comfortable with. We will have to get very, very comfortable with later for our second order stuff, especially the stuff we do with the wave equation. But for right now, I'm going to kind of put that on the shelf. We're not going to talk about it yet. But if you're interested in how this goes, this section names a couple of sections in the appendix you can have a look at. Mostly this is how to pass your derivatives under the integral sign, how to move derivatives off of a function onto another function. This is integrating by parts in multiple dimensions if you've never seen how that's done. You have seen versions of this. This is really just an application of the divergence theorem and various, Calc 3 analogs of Calc 1 theorems. So that is how this is done. But this is the derivation. The thing that results is the derivation of what's called the continuity equation. The continuity equation is one of what are called the Euler equations, which in a more general, more complicated, no, this is just a single equation, setting describes what is going on in a fluid. Now, this is not, you have to have more than this, right? So these Euler equations eventually, of which the continuity equation is just one, need to be paired with the Navier-Stokes equations, which are a second order system. So we're not going to talk about that yet, but this continuity equation ultimately that you get looks like this. So for reasons that are like historical and where this thing came from in terms of physics, the way that the continuity equation, so the continuity equation is a scalar equation. You're seeking a row of xt. X is a vector, 3 components, so this is in 3 space, and what this looks like is rho sub t plus the divergence of rho times vector v, where v is a velocity vector field. Maybe you can think about it, but you can just think more generally this is a vector field. So this is the continuity equation. This is one of what are called the Euler equations. So we will later Later we'll mention the Euler equations for incompressible fluids, of which the continuity equation is one. The Navier-Stokes equations, as I said, are a second order system that, taken all together with Euler equations, are like the system of PDEs that models fluid flow. So these are very, very complicated, entire fields of study dedicated to just studying these equations. But anyway, the reason why this warrants at least a quick mention here is just because this is actually, you remember what the divergence operator does. This is, after all, a first order PDE, right? This is a first order PDE here. Okay. So anyway, so this is just one particular example of something you see, and you say, oh, well, this is actually the same type of thing that we've been studying this whole time up until now. So that's just a nice mention of a particular application of this stuff right now. Okay. So I'm not going to mention too much more about this right now. Like I said, I may kind of do a brief survey of this stuff later, just as far as, this is kind of interesting to us, but we'll have to leave it for now so that we can get to where we're going. Okay. Now, what I wanted to talk about very briefly was the semilinear case, and the reason I say very briefly is because it turns out that the semilinear case and the quasilinear case, even though it's going to work out a little bit differently, the quasilinear case contains the semilinear case, and we're going to be dealing with the quasilinear case as well, so no reason to deal too much with the semilinear case. But what about semilinear equations? Okay, what is a semilinear equation? So recall, this means I have a coefficient function. So let's say that I am back to having two independent variables for my PDE, and I have a coefficient function on the x partial term. I have coefficient function on the y partial term. Neither of these coefficient functions depend on u. Okay, and this is equal to, rather than some coefficient functions on u and then an extra like inhomogeneous coefficient function, I have a single function c that depends on the independent variables x and y, but also possibly on u itself. Okay. So the question is, how does my method of characteristics work here? So how can I apply the method of characteristics here? Let's recall our characteristic equations, right? So our characteristic equations have us looking for characteristics. So our characteristics are parameterized curves looking like this. And the way that I do this is I say, well, like x dot of s is equal to, a of x of s, y of s, and y dot of s is equal to b of x of s, y of s. Okay, so this hasn't changed, right? If I covered up the left-hand side of this equation, this is exactly like the linear case, and so these two characteristic equations, if I follow that same analysis, it's not actually affected by this thing now being different. So then how do I deal with this? Right? This before involved the C1 and C2 coefficient functions, so how does this work now? Well, it turns out that exactly how it works is like this. Oh. How is this different? Let's quickly remember again my original characteristic equation so I don't have to rewrite them. Let me find them here. Here we go. right? So in my original characteristic equations, the first two are the same as I have written down for this. But the z was some coefficient function that only depended on this x and y times z. That's the only place that z showed up in this equation, right? And then plus some other coefficient function with x and y plugged in. So this is very different because this last ODE is something that, so previously the ODEs that we got out of our characteristic equations were guaranteed to be nice enough. Okay, but now that's no longer the case. This last ODE, if I'm not careful to give you something that's actually doable, this last ODE could be really, really nasty. Okay, this could be potentially something you don't know how to write out the general solution of. But forget about that for a second, right? We're imposing selection bias here in general in this course, meaning that when I talk about a general case that could be really, really awful, it's very important to remember that this could be very, very awful. But at the same time, it's important to realize that if we're actually going to be working through an example, it's likely not going to be awful. Or if you're going to be given an example to do on a homework or an exam, it's likely not going to be really, really awful. So it's good to hold those two thoughts simultaneously in your head. Let's see how this works in a particular example. So let's have, let's see, u sub x plus 2 u sub y is equal to u squared. That's something we weren't allowed to have before, right? And let's give ourselves an auxiliary condition specified by a function h. Okay. So notice our data curve here is the x-axis. So again, we're solving the characteristic equations. So what are my characteristic equations here? My characteristic equations are x dot of s is equal to 1 and y dot of s is equal to 2. Right? We're solving these two with initial conditions. X of 0 is x naught and y of 0 is 0, like we did in a lot of our previous examples. So doing that, this implies that these equations have solution. X of s is x naught plus s, and y of s is 2s. Right? Okay. Now, of course, z of s is defined to be this value of the value of the solution on the characteristic. Okay. And if I write out this last characteristic equation here, I would get z dot of s is equal to z squared, right? Z of s squared. Now, notice that is, here's the thing, right? Notice that you're in a situation where do I actually need to solve for x and y here to find, or to be able to solve this last equation? It seems like no, right? It seems like no. But this is an ODE that's not, this is a nonlinear ODE. This is something that can be kind of nasty to solve in general. Of course, there are some, for first order ODEs, you did learn some techniques for dealing with nonlinearity, right? So, so you do have some techniques at your disposal in a lot of cases. And so, what is a solution to this? This has solution. Z of s, which is 1 over c minus s. You can check that yourself if you like. Okay. So then the fact that this z of 0 is equal to, so z of 0 is the value of the characteristic at x sub 0, 0, which is h evaluated at x sub 0, as usual. So imposing this initial condition here, I get that c has to be 1 over h of x sub 0. And so, rewriting this in terms of x sub 0 and s entirely. Here, let me buy myself some room here. So, let's see. This means that z of s is h. Well, this is 1 over h of x naught here. If I clear denominators by multiplying through by h of x naught over h of x naught, I get an h of x naught in the numerator. And then here I get 1 minus h of x naught s. Okay. So I'm almost happy. I need to solve for, so given a generic point xy, I need to find an x naught and s corresponding to it, right, to know the characteristic that this thing lies on. And so how do I do that? Well, this is actually pretty easy here. Let's return to my equations, right? X and y are x naught plus s and 2s. So x is equal to x naught plus s, and y is 2s. And so this implies that s is y over 2. But if s is y over 2, then x naught is x minus y over 2. And so, using this form of z, I can write out the solution. So my solution is u of xy is h of x naught, so this is h of x minus y over 2, divided by 1 minus h of x minus y over 2, times s, which is y over 2. So this is my solution. So the only wrench that was thrown into my plans here was this last characteristic equation, right? This last characteristic equation is now a first order ODE that was more complicated. Okay. All right. So that's that. As I said, I'm not going to do any more examples of semilinear because we're going to do some examples of quasilinear, of course, which, you know, this is a special case. Although I should say that the quasilinear case is nice to separate out because there's something that happens going from semilinear to quasilinear that changes. So semilinear is still technically a nonlinear equation, right? But it is close enough to being linear that a lot of the kind of novel things that happen in the nonlinear case, you don't get to see them in the semilinear case necessarily. So that's why it is nice to separate these out, right, and not solely think of them in terms of linear versus nonlinear. Okay, so now I wanted to talk about what are called transversality conditions, or the transversality condition. What does that entail? What do I mean when I say that? So recall When I had the first PDE, I think I wrote down in this class, if I have constants A and B, right, and I have that PDE, A u sub x plus B u sub y is equal to 0. Remember, our method of characteristics in this very simple case had us noticing that this is more like our proto method of characteristics, had us noticing that if you specified data on a line that wasn't parallel to the vector AB, so let's look at the vector AB. So if I mentioned back then that when you specify data, right, it is of course very common to specify data on a curve that is just say the x-axis, right? So it's some coordinate axis. That's a very common thing. It's going to be more likely than not for these first order examples that we do. But I don't need to do that. I could, in fact, of course, there's plenty of situations that might arise where the data that I have is specified along a curve that's not the x-axis. And so drawing a picture here, rather than thinking of specifying the curve along the x-axis, I could think about specifying a curve or the data along a curve that looked like this. I'll call it gamma, right? Okay. But there was an issue here, right? So there was a slight issue here. How general or how bad of a curve could I specify my data on and still be able to do all the things I want to do? Well, the main thing is that we wanted our data curve to be transverse or kind of in general position of the characteristics, right, or relative to the characteristics. So maybe the characteristics look like this. This is what we wanted, right? So if here are our characteristics, and I'll say that my characteristics are, what is a characteristic parameterized as? It's parameterized as an x of s, y of s thing, okay. Well, this data curve, right, that I'm specifying this data along, I wanted it to be transverse to these in the sense that it never lined up with these things. So I had a couple of requirements, right? So I had one that's maybe a little bit more tricky to check. I wanted this gamma to intersect all of these characteristics, right? That was one of my requirements. So all the characteristics that I needed to fill out the entire plane. Why did I need them to fill out the entire plane? Because the whole method of characteristics is based on me being able to pick a completely generic point and find a characteristic passing through that point, right? And I had to be able to do that so that I can solve for this x naught and s that correspond to this characteristic that passes through this point, right, at the given parameter value, or at the parameter value that I find. And so in order to actually solve this thing, I actually require that these characteristics fill out the domain in question. Because if they left any gaps, then if I picked a point that was in that gap, I wouldn't be able to solve for this x naught and s, right? I wouldn't be able to actually find a solution at that point. And so I need these characteristics to fill out the whole plane. So that's one thing that was actually a requirement on the characteristics. Okay, but then I need this data curve to then intersect all of these characteristics, right, once. But also to do so in a way that it wasn't degenerate. What do I mean by that? I don't want gamma to be tangent to any of these characteristic curves. So the easiest case of seeing this and what happened if, and I talked about this when we first talked about the method of characteristics. I talked about this issue with the data curve. So if we specify data in a way that is not uh, uh, so if we specify data along a curve gamma that is not parallel to the vector AB, because this vector told you the direction of all the characteristics, right? So here I've drawn a picture that's more general. The characteristics are curves, but for this example, these characteristics were all lines in the direction of this vector. So I needed and if I draw a little mini picture of that, what was going on is the characteristics, I'll use red since I used red before. So the characteristics look like this. And so because these characteristics are simple, the only thing I need is that I need my curve to not be parallel to this. I need a line to not be parallel to this. But even more so, I want this to work in such a way that not only do I want this to not be parallel, so that's a simple example, have a data curve that looks something like that. But if I had a more general data curve, I don't want this to like be tangent to any of these characteristics, right? Okay. So there's some condition on the tangent vectors here. Of course, talking about each characteristic as a curve, the tangent vector is easy to see. It's just this. But then computing the tangent vector of the characteristic, well, I have to compute the tangent vector in the same way that I would for a parametric curve. Okay. So if we have done this in a way that is not parallel, say, to the tangent vector of these things, we call that non-characteristic data. So if gamma is not parallel to any of the characteristics, we say we have non-characteristic data. Okay. And this condition that guarantees this is called the transversality condition. So what is the transversality condition in this case? If I have a characteristic, right, that is x of s, y of s, this data curve I can parameterize. I want to use a different parameter because this parameter for this curve is not going to correspond to the parameter s. So I use a different parameter, and I'll use the parameter tau. So x naught tau, y naught tau is what I'll call it. And I'll use the subscript 0 here because, of course, this curve is typically corresponding to the parameter value s equals 0 for the characteristic. And so, of course, we require that it intersects all of these projected characteristics, if you like. So that's one condition. And we want it to not be parallel at any of these. And so what we want is we require that the tangent vector of gamma, so gamma here again is x naught tau for some x naught, y naught tau for some function y naught. We require that the tangent vector of this gamma is not parallel to the tangent vector of the characteristic which passes through the point x of s, y of s, which passes through the point x not tau, y not tau. So here we're thinking of tau as parameterizing this entire curve, but for a given tau, for a given value of tau, we want to think about the tangent vector of this characteristic that passes through this point here. But what is this? So first of all, what's the tangent vector? So tangent vector to gamma. This is a parametric curve. I don't care about it being a unit tangent vector. So the tangent vector is obtained by just taking the derivative in each slot. So the tangent vector to gamma is x naught prime tau, y naught prime tau. Right? What's the tangent vector to characteristic passing through the point x naught tau, y naught tau? Well, I have the characteristic equations, right? X dot of s and y dot of s are a of x of s, y of s, and b of x of s, y of s. This is for a completely general, like, linear equation. So here, I'll rewrite linear equation here. All right, something like that. I mean, no, I don't need this to be 0. This can be completely general here. Okay. All right. So the characteristic equations actually tell me that the tangent vector to the characteristic passing through here is x dot y dot, but that's just a with x and y of s plugged in. But here I'm looking for specifically the characteristic passing through this point, and so it is actually a of x naught tau, y naught tau in the first slot, and b of x naught tau, y naught tau in the second slot. And so the tangent vector to the characteristic is a of x naught tau, y naught tau, and b of x naught tau, y naught tau. I know I'm running out of paper here. So I have two vectors, right? And I want them to not be parallel. So what's the condition then? I.e., I want the determinant of the matrix. I'm going to take those two vectors and put them as columns here, and I want that determinant to be non-zero. So here is for the characteristic tangent vector. And here is for the tangent vector to the data curve. And I want this determinant to not be 0. That's my transversality condition. Okay. This is my transversality condition. Why did I go through the hassle of writing all this? So this allows us to make some statements about our data and how it's specified, and to be precise when we want to try to talk about, say, the existence of a solution locally. What do we mean locally? So we know that there's no, like, global existence and uniqueness theorem for PDEs in the same way that there are for ODEs. I already told you that maybe in like the first lecture or maybe second lecture. But here the idea is that if we're careful with how the data is specified, in a lot of cases, if we're lucky, we can get a sort of local existence of solution, and local meaning in a neighborhood of this curve, meaning in some, of course, I'm not implying that the curve ends here, this would go on forever, in some region of the plane that contains the curve. Okay, and this is so long that this transversality condition is satisfied, and we're, there's some other nice things going on. But here's, this is basically a reason for writing something like this. I can make some nice general statements about the existence of a local solution. And this we can do so long as the coefficient functions are smooth enough. So I think even C1 is fine here, but but certainly if there's enough regularity on this coefficient functions, we can actually prove existence of a local solution in a neighborhood of that data curve. Okay, and the nice thing here, right, is to remember that even if the transversality condition is satisfied at all places where they intersect, maybe my data curve doesn't intersect like all of the projected characteristics. That's also a possibility. Right, that could happen. But nevertheless, we can, if we have enough regularity of the coefficient functions, we can actually prove existence of a local solution nearby this this data curve, or in a neighborhood of this data curve, which is nice. Okay. Now, before we do the general quasilinear case, we are going to do a nice quasilinear example that is very instructive concerning what sort of issues arise in the nonlinear case. In fact, it's so instructive that the textbook demands in bold letters that you not move on until you have understood the pictures that are drawn in this section. And I think I agree, because it is actually extremely helpful to understand how this works, because this kind of hints at a lot of the complications that arise in the nonlinear case, and this is one of the most basic examples to see this, and it's a really nice example where you can kind of understand everything that's going on. So, first of all, let's go back to our transport equation. So recall our transport equation. Just the simplest one with constant speed. There it is. Say that we have specified this initial signal, right? That's how we thought of this. Now, what is it that this looked like? Recall the profiles, right? So the profiles are profiles of this solution, right? X versus t here, where we had, for fixed t, we thought of this. So for fixed t, we had the following. So say that our g of x is a signal. We like to think of it a lot of times looking like this, right? let's say that this was our profile at t equals 0, right? All right, so this is actually g of x itself. Yeah, I'll just write x here. Then what did we see about how this thing behaved, right, for different t values? So what was the profile at like t equals 1? This maybe looks something like that. And then at t equals 2, maybe it looks something like this. And so on. And so this was the transport equation, right? Maybe this should have been moved a little bit further to the right. It was the transport equation in the sense that it was transporting this signal, right, in this fashion. If I plotted a bunch more of these profiles, it takes this initial shape, right, specified by this function g, and it just transports this shape along, right, at this constant speed, right? The c was the speed of the transporting. Okay. Now, if we interpreted this picture as telling us like how a wave might move, right? So imagine we're at the beach, we're watching the waves come in and crash on the shore. The question is this like an accurate model of how like a wave, for instance, would say approach and then crash on the beach? Well, the answer is no, right? The wave doesn't just keep its shape the entire time as it's approaching the shore and then just crashes into the shore. That's not how it works, right? So this is not going to be any kind of good model for that sort of behavior, right? What about when we considered the variable coefficient case? So what about the variable, or sorry, not the variable coefficient. I mean, yes, it is variable coefficient, but variable speed specifically. So what about the variable speed case? Let's look this up. All right, let's recall this. So recall the variable speed transport equation. What was the variable speed transport equation that we considered? U sub t minus x u sub x is equal to 0, and u of x naught is equal to g of x. We just did this yesterday, right? So we just did this in the last lecture. And if we thought of g of x as a blip, what did the profiles look like? They look like this, right here. Here's what my profiles look like. This was the effect of this variable speed on this transport equation transporting this blip signal. Okay. Does that look like how a wave on the beach works, right? No. Right? How does a wave on the beach work? Right? How does this work? Well, how a wave on the beach works is something like this, right? You have a wave, you have the top of the wave kind of building up, and then eventually the top of the wave kind of crashes over the bottom, right? It overtakes the bottom and the wave breaks. Okay, that's how the breaking of a wave works. But that's not exactly, or that's not even close to either of those two examples we just showed with the transport equation. So, what is it that we can do to model this wave thing? What about the following? And this is known as the Inviscid-Burgers equation. The textbook, I think, just calls this Burgers equation, but this is technically the Inviscid-Burgers equation. This is u sub t plus u sub x is equal to 0. So in the transport equation, if we thought of this as telling us speed, right? So here we had constant speed. Here we had variable speed. Then here, because of this u term, right, this is saying that the speed of the transporting is like proportional to the value of the solution, right? So the speed of transport is not just variable in the sense of previously. Here it was variable, but it only depended on the spatial variable x. Here the speed of transport is proportional to the value of the solution itself. So just take a second to think about what type of equation this is before we move on. So what type of equation is it that's going on here? Well, it's first order, okay, clearly. It's definitely nonlinear because of this term, right? So the coefficient function on the use of x term involves a u, right, which previously wasn't allowed in either the linear or semilinear case. This is quasilinear rather than fully nonlinear because fully nonlinear means that my functions involved are allowed to be functions of the partial derivatives. So it's not quite that bad. I still have coefficient functions on these partial derivatives. The partial derivatives themselves are not being touched by a function. You know, this is not u sub x squared or something like that. And so instead, my coefficient functions now, at least this one, depends on u. This is the example of a quasi-linear first order PDE. Okay. So it's definitely nonlinear, and it's nonlinear in a way that is more severe than the previous semilinear example that we did. Okay. And so, how do I go about doing this? Let's try to do this with the method of characteristics as we currently have it. Right, so we have the PDE that looks like this. So this is u sub t plus u sub x is equal to 0, and then I have my initial blip, if you like, or my initial data specified as function g of x. So just like we did previously, because this is a time-dependent PDE and the coefficient function here is 1 for the t, I can think of t as the parameter of the characteristic, right? And so the characteristics that I seek look like this, right? This is my usual trick. Okay. So how would I go about, so of course, like I said, the first characteristic equation is easy because it's just t dot of s is equal to 1, which tells me that s and t are the same. Okay, of course, because I'm specifying on the t equals 0 axis here. What about the other characteristic equation? So the other characteristic equation would be, since I'm using t as my parameter now, I can write this as dx dt rather than dx ds. So this would be dx dt is equal to u. That is how I would set up that characteristic equation. But how would I deal with this, right? So I have to be careful here, right? Recall that z of t now is going to be u on the value of the characteristic, so it would be u at x of t. So I could rewrite this as follows. I could say, well, this is dx dt is equal to like u at x of t, so u at the on the characteristic. So this is just z, right? So maybe I should say dx dt is equal to z. But what's the problem with this? Typically, the way that the method of characteristics works, or worked for us, was that we would solve the characteristic equations here in t and x. The one for t is easy. The one for x, though, if it involves the z, that's kind of an issue here, because I was using the solution to the first few characteristic equations to get me the solution to the last ODE involving z. But here, the unknown z is showing up in this characteristic equation for x, and that's a problem, right? At least it seems like a problem that I don't really know how to fix. So what do I do instead, right? So how do I go about fixing this, right? I don't know z. I don't know what z of t is. That's the entire problem, so I can't solve this. So I seemingly cannot solve this. Well, of course, the method of characteristics we developed so far applies to linear and semilinear, right, as we've seen. So we're going to have to think about what to do in this quasilinear case. But before we get there, for this particular example, let's try something else. So here's the first thing. The question is, what is dz dt? Why am I asking? Because this, if I thought about writing my characteristic equations, let's try to write my characteristic equations here as kind of naively, right? So the first one is the one for t, so this would be, you know, t dot of s is equal to 1, right? And then the next one would be x dot of s is equal to, so here's where I want to replace this. So t dot s equals 1, this tells me, also because I'm specifying on the t equals 0 axis here, that s and t are the same. So this tells me that s and t are the same. So from here on, I can replace, for the rest of the characteristic equations, I'm going to replace s with t. So then x dot of t is z of t, would be my second characteristic equation. But I couldn't solve that. So then what's the last characteristic equation that typically I need to solve the first few before I even have a hope of solving this? So the question is, what is this? So that's why I'm asking this. What is dz dt? Now, you might say, well, if we look at the PDE and we follow how this worked before, let me find my sheet, then in the semilinear case, of course, this was just this z dot of s was equal to the function on the right-hand side that could possibly involve u here, right? Well, here that function is 0. So the question is this just z dot of t is equal to 0? Is that true? So let's actually compute this, right? So if z of t is u of x of tt, then dz dt is d dt of u of x of t t. I'm going to write the t derivative first. So how do I compute this derivative, right? This is chain rule again. So this would be u sub t times the derivative of t with respect to t, which is just 1, plus u sub x times the derivative of x with respect to t, oh, wait. This dx dt, remember, we wanted to kind of naively write it as dx dt is equal to u. We were able to recast that as dx dt is equal to z because, you know, z is the value of the solutions on the characteristic. But really, this is dx dt is equal to u here. And so what I get is u sub t plus u sub x. You might be tempted to write that this is equal to 0, but let's think about the logic for a second. Okay, so in order to be able to write that this is equal to 0, what do I need to assume in this whole process, right? Before I get the gears rolling, what do I have to assume? I need to assume that there is a U that solves this, right? So I'm not saying that I know how to find it. I just say that it exists, right? So I say there is a U that solves this with auxiliary condition. And if I assume that that is the case, right? I'm not going to prove that right now. I'm not going to find it. I'm just going to assume that it exists. Let U be equal to that thing, right? Then in this process, once I get to this step, if U is the thing that solves it, then this is equal to 0. Okay. That might seem like a kind of a weird thing to focus on, but it's important because we have to keep clear the logic here to realize what it is we're actually showing, right? Because it could be that that initial assumption was bogus, right? That initial assumption might not be the case. We have to think about how we justify these things. But anyway, let's say that there is a solution. We're trying to find it, and that U is that solution. So we get to this point, and dz dt is in fact equal to 0. So the answer to this question is dz dt is equal to 0. But what does that mean? Right? What does that mean? It means, remember, because our characteristic can be written in this way, it is often common to just think of the characteristic as a scalar valued function x of t, right? Since we can definitely do this in the t versus x world, we can write it like this. So, and of course, the way that I think about my characteristics being graphed, this is already how I've been drawing them, right? Okay. So then what this means, if dz dt is equal to 0, what this means is that the characteristic, or the along a characteristic that solves this ODE, we'll call this asterisk. So what this means is that along a characteristic x of t solving this asterisk differential equation, the value of the solution is constant. So that's a huge thing that we've shown, right? So along a characteristic that solves this differential equation we set up here, the solution has to be constant. That's what it means, that dz dt is equal to 0. Okay. But what does that mean? Since the solution is constant along such a characteristic, then the right-hand side of the PDE asterisk here has to be constant. Because this right-hand side is just the value of the solution along the characteristic. If dz dt is equal to 0, then along a characteristic solving this differential equation that gets me here, right? It's because of this step, this dx dt is equal to u step. So along a characteristic that solves this differential equation, this computation tells me dz dt is equal to 0, which means it's constant along such a characteristic. But since this solution is constant along such a characteristic, going back to this differential equation, it means this right-hand side is actually just a constant. So then dx dt is equal to a constant. So I have characteristics x of t, and their derivatives are constants. Well, what kind of curve is that? It's a straight line. The characteristics must be straight lines. Whoa, so that's like two huge revelations here, back to back. So along a characteristic, the value of the solution is constant, but also the characteristics themselves, by very quickly realizing what this implication means, that dx dt is a constant, and x of t is the function that is my characteristic, right? So the characteristics have to be straight lines because they are graphs of functions that have constant derivatives. Okay. Now you might say, wait, but actually that's exactly what happened in the original transport equation. So we actually have kind of the same thing going on here. But there's a key difference. So now this is actually what happened for the OG transport equation. But now there's a huge difference. What is that? Well, let's go back and think about this. The solution is constant, but that constant is dx dt, which is the slope of the line tangent to the characteristic curves. But wait, the characteristic curves are straight lines. So the line tangent is just the line. So this constant is the slope of the characteristic lines. So the solution is constant along characteristics, but the characteristics are lines with slopes determined by that constant value. Of course, specified on the t equals 0 axis, that constant value is given by the value of g at the point. That in itself is a big, huge difference, okay, as we'll see. So I'll go ahead and say what this implies, and then we'll talk about this here in a second. But what this means is that the structure of the solutions here, the structures of these I should say the structure of the characteristics here is actually determined by not just the PDE, but also this auxiliary condition, right? That is different than the linear and semilinear case. And the reason why you can immediately see that it's different is go back to any of those linear and semilinear examples. Well, we only did one semilinear example. Go back to those linear examples we did, or look at this from your exercises in homework 1, and you'll see, oh, wait, right? I could have actually discovered what the characteristics look like just by looking at the PDE itself. I don't need to reference the initial condition at all, right? I can actually just look at the PDE itself, ignore the initial condition. I worry about that when I'm finding the solution, but to actually find the characteristics, right, what the characteristics look like, I don't need to refer to that at all for linear and semilinear equations. But now we're going to see that this is no longer true. Okay, this is no longer true. So the characteristics must be straight lines, but along those straight lines, the value of the solution is constant, but the constant is determined by, or the constant is the slope of those lines, right? So what is this big key difference? It's that the slope of the characteristic line is equal to the value of the solution takes on the line, which of course is going to be constant. So the value the solution takes along the line. Okay. So then, here is the key takeaway. So since the solution is known at the point x naught 0, right? In fact, we know exactly that u at x naught 0 is equal to g of x naught. So we know exactly what it is at this point, right? Okay. Then the solution must be equal to this same value, right? Must be g of x naught along the entire characteristic line emanating from that point. But this line is the line passing through x naught 0 with slope g of x naught. Think about all of the implications here, right? This is a much more complicated thing that is happening here. It's unfortunate that it's more complicated, but that's just kind of how the world works. Unfortunately, a lot of the most interesting phenomena are actually nonlinear, so there's no getting away from this kind of thing. But here, like I said, is perfect encapsulation of some of the things you get with nonlinearity. So this is what it is that's going on. Now, what this means, as I said, is that the function g actually influences, right? So g of x influences the structure of the characteristics. Okay. So, in fact, right, like, let's see what happens if at a point, right, x naught 0, the characteristic line through this point is the line with slope g of x naught. So slope, so this line has slope with respect to t equal to g of x naught. Okay, so this is slope with respect to t. So this is like if this is x and this is t, we're doing this in the opposite way. We're doing this as run over rise instead of rise over run. Okay, that's fine. Okay. And so the slope with respect to t is g of x naught. So then what would this look like for different g? So suppose g of x is increasing. It's an increasing function of x. Then what would maybe a few characteristics look like? Well, maybe the characteristics would look something like this, right? So remember this slope again is with respect to t, so it's like it's the reciprocal of the slope that you're used to when you typically see plane like this. So then say that when this is closer to 0, maybe like emanating from this point is a line that is closer to being horizontal with respect to t, okay, or vertical drawn like this. And then here, maybe it's getting a little, the slope is getting greater with respect to t. So, and maybe here, maybe here, it looks like that. So each of these are a different x naught, right? And if g is increasing, then the slope, again with respect to t, is increasing, and so it looks like this, right? So we start out with a slope that's near 0 with respect to t, right? Here, maybe I'll add another point here that's like, okay, so we start out with something that's like near 0 with respect to t, and then we get something like this, okay? Now, if this is the g that we have, then notice that these characteristics, they all intersect this t equals 0, x-axis once. They don't intersect each other, which is required, right? And they fill out, right, the entire upper half plane here. So we're happy here. We're happy in this case. We should be able to solve this equation, find a solution that is defined for all t greater than or equal to 0 here, and we should be able to do this in an analogous way that we use the method of characteristics the entire time. But what happens if g is, say, decreasing, right? What if g is decreasing? So what if I have like an x naught here, and we'll say that the slope of this x naught is, with respect to t, it gives me a line that looks something like this. Okay. Well, if I have a decreasing function, then maybe at this point, now the slope of my line looks something like this. So what's the problem here? Characteristics at some point intersect or collide. Why is this a problem? So this might remind you of the various facts that were stated about trajectories for these existence and uniqueness problems back in ODE. The reason why these trajectories can't collide, right, and for you to have a nice, well-defined solution everywhere, is as simple as this. We are claiming, right, let's go all the way back. The slope of the characteristic line is the value the solution takes along the line, right? So you have solution known at your initial point. That solution has to be equal to that initial data function evaluated at that point along the entire characteristic line. So here, u has to be constant along this line every single place. U has to be constant along this line at every single place. These two slopes are different, meaning that along this line, u has one value. Along this line, u has a definitely different value. But if they collide, then at this point of collision, this point lies on both of these lines. So at this point, your solution u would have to have, say, this slope, right, whatever value that is. But this point also lies along this line. So at this point, not only does it have to have this value, it has to simultaneously have this different value. Your solution is multi-valued. Your solution is over-determined, right? At such, or in such situations. The solution is over-determined. And I run into, and I am unable to find a global solution on a domain where this happens. So maybe I'm able to find a solution on like a strip of the domain, a piece of it, but now suddenly I have issues here. The characteristics collide. And this is the first example of this happening. Okay, so this is the cost of nonlinearity here, right? This is the unfortunate fact that the nonlinearity forces this sort of thing to be a possibility, right? So again, notice that it was possible through a judicious choice of G, right, to make this actually all work out fine, right? So it was possible for to choose a G where this all worked out okay, but this also tells you there's this weird interplay, right, where the auxiliary condition massively influences this behavior. There's an interplay between the PDE, the characteristics, in a way that wasn't there for linear and semilinear equations. Right? So again, just to stress, for linear and semilinear equations, you were able to determine the form of the characteristics without reference to the auxiliary condition. Here, that wasn't possible, right? The auxiliary condition told us whether we were in a case like this, where we were happy with how these characteristic lines looked and they didn't collide and everything was good, versus this sort of situation where the characteristics can collide. So anyway, that is that. I think that's a good stopping point for today. I'll beat this example into the ground a little tomorrow because it's very important. We will talk about general quasilinear equations and do a few examples. And I may dip my toe tomorrow into, if we have time, we might not have time tomorrow, and I might do it the lecture after instead. We will at least give you a form of the completely general case for fully nonlinear PDEs, and I will do at least one good example just to show you of how amazing this kind of thing can be if you're very particular and choose very, very nice examples where everything works out. So anyway, that is the deal, and I will see you all next time.